Hi everyone, let's have a discussion on inductance of three-phase line with unsymmetrical spacing but transposed. Okay, unsymmetrical spacing, we have to transpose the lines. Okay, we have to see in this topic. Previously, we have discussed symmetrically equidistance three-phase line inductance. Right? So this is not enough important topic here. Okay, see three-phase lines with unequal distance and unsymmetrically spaced here. See the diagram of that. Three-phase overhead line. Here, three-phase line conductors are not equidistant from each other. The conductor spacing is said to be unsymmetrical. Okay. Under such conditions, the flux linkage and inductance of each phase are not the same. A different inductance in each phase results in unequal voltage drops in the three-phase even if the currents in the conductors are balanced. Okay. Therefore, the voltage at the receiving end will be same for all the phases. In order to make the voltage drops are equal in all the conductors, we generally interchange the positions of the conductors at the regular intervals along the line, so that each conductor occupies the original position of every other conductor over an equal distance. Okay, that is whatever explanation for this diagram, right? See here, in order to voltage drop are equal, we generally interchange the position of the conductors. At the regular intervals. Here x here, next second position. This is first position, second position, next third position, like this. Okay. So that each conductor occupies the origin position at every conductor over an equal distance. Such an exchange of position is known as transposition. So that the balance in the three phase is restored here by means like this transposition. The conductors in the individual phases are denoted by here x, y, z. First position here, second position and third position, where the position are given 1 to 3. The same average inductance over the complete cycle is obtained due to the transposition. Okay. So here first x conductor is placed first position, next x conductor is added second position, next x conductor is added third position. So the flux for the x conductor is the that is nothing the sum of average of first position, next second position, next third position. Okay, we have to take the average of all three positions. So that by finding the flux linkage of the conductor for each position here, first position, second position and third position, during the complete cycle of the transposition. Okay, for like this x conductors, we have to do for the y conductors. Y conductor is second position, next third position, next first position. So average is what? First position, second position, third position all together. And also here z conductor is here third position, next it is shifted to the first position, next it is shifted to the second position. See the average of the flux of the conductor z is summation of third position, first position, second position flux. Okay, so the average gives the again first, second, third like this position. Okay, so we have to consider here first x conductor which is placed at the first position. First, we have to write the equation for the first position conductor flux. Next, go for the second position, and next the third position. See, okay. See here, already you know the formula for the flux linkage. Flux linkage of the x conductor is at the first position. Y conductor is at second position. Z conductor is at third position. See, flux of x conductor, one indicates x conductor, one indicates conductor x is at first position. Okay, is equal to 2 into 10 to the power minus 7. X conductor current is Ix, ln of flux of itself, next flux due to Y conductor, next flux due to Z conductor, right? So here flux itself means its radius 1 by R plus flux due to the Y conductor, whatever current flowing through the Y conductor, it gives the flux linkage to the X conductor. Next, Iz current flowing through the Z conductor, it gives the flux linkage on the X conductors. Therefore, see from the figure, the flux at the X conductor is equal to flux of itself X conductor, flux due to Y conductor that is Iy current flowing here. Next, Iz current flowing here, it gives the flux links on the X conductor, right? Therefore, see, its distance of its self-conductor flux is nothing but its radius. Next, plus distance of while taking the flux due to the Y conductor, we have to take the distance, right? We have to take the distance here from go according to the order 1, 2, 2, 2, 2, 3, 3, 2, 1, 1 to 2, 2 to 3, 3 to 1, like this. Okay. See, next Y conductor gives the flux on the X conductor. Therefore, distance between them here 1 to 2. It is not 2 to 1, it is 1 to 2. Okay, order is 1, 2, 3, like this. Next, conductor Z also produces a flux on the X conductor. Okay, flux due to the Z conductor. Distance between them is 1, 2, 3 or 3 to 1 here. Order is, how is the order? 1, 2, 3, 3, 1, 2, 3. See here 1, 2, 3 we can't take it because order is 1, 2, 3, again 3, 1, 2, 3, like this. Okay. So distance from X to Z is 3 to 1. Okay. 1, 2, 3, 3, 1. So distance between X and Z is 3, 1. Getting? So see here itself flux, that is the distance is 1 by R dash. Then due to the Y conductor current I by, for the Y conductor, distance between X and Y is 1 to 2, order is D1 to 2. Next, due to the Z conductor, that is Iz current flowing through that, produce the flux on the X conductor, that is distance between them is D3, 1. It is not 1, 3, 3, 1. Okay, 1, 3 it is not order. 1, 2, 3. Next 3 to 1. Okay, so order should be to take here 3 to 1. Next, so it is the what flux of the X conductor when it is at the first position. Next shift the X conductor to the second position here. X is the second position, Z is the first position, and Y conductor is at the third position. Next, take the flux of the X conductor. Total flux here is equal to what here? Flux at the second position psi x2 is equal to 2 into 10 power minus 7. Next, current here is Ix, ln of 1 by R dash of X conductor flux, plus next due to Y conductor, that is current is Iy, ln of 1 by distance of this Y conductor to the X conductor. You have to take, how to take here? Order is 1, 2, 3. It is should be 2 to 3. Okay. 1 divided by 2, D, 2, 3. Right. Next, flux due to the Z conductor on X conductor. You have to take the distance. Here is 1, 2, 3. Don't take from X conductor to Z. Should be order distance from position 1 to 2. Therefore, 1 divided by D, 1, 2. See here this. See, due to Y conductor 1 divided by D 2 to 3. Next, Z conductor D 1 to 2. Getting? Next, similarly, X is at the third position, Y is the first position, Z is the second position. See, X conductor is shifted to the third position, Y is first position, Z is the second position. Next, find the flux of the X conductor at the third position, that is psi x3. See here. Flux of the X conductor X position is third position. 2 into 10 to the power minus 7. X conductor flux, that is Ix current through the X conductor, radius itself only. Then due to the Y conductor, Iy, distance, due to Z conductor, Iz, and distance. D3 to 1, here D2 to 3. See here, X is at the third position. So, due to the Y conductor, flux at the X conductor position, distance is what here? 1, 2, 3, 3, 1. So it should be 3, 1. Okay, distance it should be in the order 3 to 1. Next, due to the Z conductor, the flux on the X conductor, that is D 2 to 3. Therefore, for this X conductor, see the formula for that flux. Then next conductor at the third position, D3 to 1 here, D2 to 3. Getting? Order how to take while writing the distance between the two conductors. Okay. This is the what flux of the X conductor at the first position, second position, third position. Next, total flux of the X conductor is the average of these three. Flux at the first position plus second position plus third position divided by 3. That is the average flux I have to take here. Total flux of the conductor X is equal to first position, second position, third position divided by 3. So add all the three equations. Common is 2 into 10 to the power minus 7. This is divided by 3. Take it common here. So add all flux of the X conductor, internal flux itself only, that is all 3 means 3 into the 3 Ix ln 1 by R dash plus, okay, Iy take it common, Iz take it common here, that is remaining is inside the bracket, add all 3's, okay. Here is Iy into this term, Iz into this term. See here ln of this term plus ln of, all these three are adding, right? So take it ln common here. It is ln of 1 by d1 into 1 by d23 into 1 by d31. Here also. Is it these ln terms both sides are same? Okay, take it common ln term and Iy plus Iz. Separate it. Okay, Iy plus Iz, it is a common. Therefore, all three Ix, Iy, Iz should be balanced equal to 0. Iy plus Iz is equal to minus Ix. Put Ix equal to here. Okay. Next, minus Ix of this term. Ix here common, Ix is common here. 3 take it inside, 3 get cancelled. 1 by 3 take it here, 1 by 3. So this 1 by 3 take it a power of this term. That is raised to power means you have to take the cube root. Okay. So here a flux of X conductor is so 2 into 10 to the minus 7. Ix common, take it ln of this 1 by R dash into this term. Okay. So the flux for the X conductor is total flux is 2 into 10 to the minus 7. Ix ln cube root of d1 to 2 to 3, 3 to 1 divided by radius of that. Okay. So next, this is the what for the X conductor, same like this. You do it for the Y conductor and also Z conductor. Okay. Flux. Here next is the inductance of the X conductor. Inductance is equal to flux divided by current of that conductor. Flux of the X conductor, flux of the current of the X conductor, flux by current. Therefore, Ix get cancelled. This is the total flux of the X conductor. So I am taking this cube root of d1 to 2 to 3, 3 to 1. This is the d equivalent. Okay, this equivalent distance between all three conductors. Okay, so this is what X conductor inductance. See, this is unsymmetrical case.